Cool. All right. Hello, everyone. As you heard, my name is Henny. I am an assistant professor at Carnegie Mellon in the Robotics Institute. I'm super interested in a lot of different ways that human behavior can be used to improve human-robot interaction. But today I'm going to talk specifically about social navigation. So because not everybody is necessarily as obsessed with social navigation as I am, I'm going to motivate the domain area for you first. So here's a video I'm just going to replay. It is actually a promotional video put out by a company called Tug that does hospital delivery robots. This is their video, not mine. And can anybody tell me what is wrong with what's happening in this video? Yeah. Yeah. Yeah, exactly. So this is first-person view of a hospital robot, and it's very helpfully delivering things and maintaining the right side of the corridor, which is great. But it doesn't do social navigation. It's causing a user who's using a walker to have to move out of the robot's way. So obviously, that's not the kind of behavior that we want out of our navigating robots. We want our navigating robots to be efficient and safe, of course, but we also ideally would have them follow desirable behaviors like social norms, like yielding to somebody who has more difficulty navigating than you do. And that is the principle that drives a lot of our work on social navigation. Now, there are many, many algorithms that have to do with social navigation and how we should create robots that are successful at that. And I'm not going to talk about any of them today because this is a benchmarking workshop. So I'm going to talk about how we evaluate those algorithms rather than how those algorithms actually are executed. So let's say that we have some algorithm for robot navigating that takes in sensor data and is able to responsibly move around in the world. And the question is, how do we assess this algorithm in the best possible way? So ideally, we would have a robot that's out in the real world over hundreds and hundreds of trials with many, many people in scenarios that are reasonably logically valid, so similar to what we would expect the robot to be working with, and we would be able to collect objective metrics like how long it took the robot to take the path, and subjective metrics, so we'd be able to interview everybody who interacted with the robot. And I don't have to tell HRI researchers that that is not possible. So instead, we have to do other kinds of evaluations. And there are two big kind of camps, or two big ways of achieving these evaluations of these kinds of algorithms. One is to use data sets. So there are many open source data sets of human navigation. A lot of them take this aerial view, and you can compare your robot's navigation to what a human in this data set does. So you replace one of the humans with a robot, you run your algorithm, and you see how similar your robot was to a human in that same scene. The challenge here is that you don't get, there we go, now I have my notes, is that you don't have interaction with the robot. So the people in the environment are not interacting with the robot is not interacting with the people in the environment. The second way of achieving this is through using simulators. Simulators are great, as we've heard, are great tools for benchmarking algorithms. You can create simulators of people moving around, put your robot in that simulation, and then assess with whatever metrics you want how well that robot is doing the navigation. Now, the problem with simulators, it's very precise. You can run the algorithm repeatedly in the same kinds of scenarios, but it relies on us having a good sense of how to simulate human navigation. And so we have a chicken and egg problem here, right? If we knew how to simulate human navigation, we wouldn't need to assess our social navigation algorithms because they'd already be good. So the navigation algorithms that we're using in these simulators tend to be simplified and don't really fully represent what humans will actually do. So some of the work we've done in our lab is looking at how we can take the best of both worlds. So combine the realism of data sets with the practicality of simulation to assess social navigation algorithms. And in collaboration with these fantastic people, we've introduced this framework called SOC-Nav Bench, Social Navigation Benchmark. And SOC-Nav Bench is designed to interface with navigation algorithms. It consists of a simulator that is based on real data set of human movement. It allows you to play your robot algorithm or your robot algorithm through a series of simulated environments, and then automatically output some metrics and also videos for you to look at. So let me go into these different parts in turn. One of the cool things about SOC-Nav Bench is that instead of relying on simulated humans to do the navigation, it actually takes the navigation data from open source data sets. We have 4 different large data sets of people moving around in various outdoor environments. We then rendered those scenes and so basically took each human point, created this point map, created the environments to match what we were seeing in the camera, and then we can render those with assets, with human mesh assets, to provide both RGB and depth data to your navigation algorithm. So your navigation algorithm relies on sensor data, and we get realistic-ish, because this is too perfect, but realistic sensor data to your navigation algorithm in order to do the navigation that it needs to do. Like I said, SOC-Nav Bench automatically outputs a number of useful metrics. Here are some examples of them. So we can think about metrics that exist on the meta level, like how often the robot made it from the start point to the goal, how often it collided with pedestrians. We can think about metrics that are specifically about the robot's path. So how long did it have to traverse the path? How irregular was the path? So how often did it have to deviate from its direct heading? Things like the quality of motion, so average speed, average acceleration, average jerk, energy expenditure, right? With the idea that we want to minimize how much energy, how much battery the robot is using, and also metrics related to the pedestrians themselves. So how close at any point during the scenario did the robot get to the nearest pedestrian, and what was the minimum time to collision, which is related to how close it got, but also has to do with speed. So the minimum time to collision for any pedestrian over that run. And we can run, we have a number of different simulated situations where we can compare these different algorithms. So here's an example of comparing 4 different algorithms. The obviously the teal circles, light blue circles are pedestrians. We have the robot start here and at the goal, and we're comparing 4 different algorithms, pedestrian unaware, with 3 different social navigation algorithms. If the robot gets a red dot on it, it means that a collision has occurred. And you can see that we can run these different algorithms in the same scenario, compare our metrics across the 4 different algorithms. So here's another example. So the SOC-Nav Bench will put out not just data, not just these videos, but also these data points. So you can look at how much energy was used over the run for each of the algorithms. Here in this case, Orca, which is a really popular navigation algorithm, uses relatively less energy than a lot of the other ones. We look at how long the path was. Interestingly, here, Orca has a very high variability on the path length. This makes sense because it's kind of doing a reasonably good job of avoiding collisions, but that often requires it to go out of the direction of its movement. And because one benchmark or one simulator is not enough, 2 simulators are better than 1 simulator, we actually joined forces with Marinelle Vasquez and her group at Yale to combine their simulator for social navigation, Sean, with our simulator for social navigation, SOC-Nav Bench, to produce Sean Nav Bench. The nice thing about Sean Nav Bench is that it has even better visual fidelity. Sean was really concerned with the visual appearance of the navigation. It has many more environments, including indoor environments like warehouses. And it now, SoftNav Bench is purely based on this replay of data. ShawNav Bench also allows you to have simulated trajectories, which I said before we didn't want, but actually it can be helpful as a comparison point. And so you can find out more about that at this website, which is a conference, a workshop that they ran at Ross last year.
Where does the Sean come from?
It's an acronym. It's an acronym.
Okay. I'll say I didn't see anyone named Sean.
Nobody named Sean. Sean is our, yeah. Go to the website. Okay, so to summarize a little bit what I just talked about before I move on to my next point, we have these SoftNav Bench, which allows us to benchmark social navigation using both data sets and simulations. So data sets alone provide us with realistic human movement, but are not interactive. Simulations can be interactive and repeatable, but they don't necessarily provide realistic motion. And so SoftNav Bench tries to get the best of both worlds by turning our data sets into simulations, simulated scenarios, and automatically outputting a suite of relevant metrics. And it has this very nice API so that any algorithm that takes in RGB and or depth data can operate within those environments, just like it would in the real world. So until now, we've been talking just about the robot, but the reality is that, we care about the metrics of the robot's performance, but robots exist in human spaces. And so we're also interested in the experience of the humans, not yet the canines, maybe someday, but we're interested in the experience of the humans that are navigating around the robot. And the reality is that social navigation is not just about how well the robot does, it's about how the people who are embodied in that environment, interacting with the robot, are experiencing that robot's navigation. So this top-down view is sort of misleading because social navigation is experienced as a first-person perspective. So we're also looking at how we can develop ways of understanding the user experience when robots are navigating in our environment. Again, we turn to simulators, and we are investigating using these kinds of realistic simulations that allow us to take a first-person perspective to measure how people can interpret a robot's movement through space. In this case, we have a restaurant scenario where people are trying to decide, is this robot server coming to me or is it going somewhere else? It's a very important decision. We actually collected data on using this kind of, that's not my mouse. We collected data on using this kind, that's not your mouse.
No, it is.
Oh, is it? Oh, huh. I thought it was in the video. On making this assessment from the first-person perspective. So we ran 300 people on an online study where we showed them various first-person perspectives of different scenes like this. And we had them continually move the slider where they would move it either toward my table if they thought the robot was coming to them, or towards other table if they thought the robot was going somewhere else. And by having them continually slide this, this slider around, we get a continuous measure of their interpretation of the robot's movement. So let's say that the robot was actually going to the other table. We can graph this over time as how much they are correct or incorrect, how certain they are about the correct goal versus the incorrect goal. So if at first they think the robot's going to their table, they start to be incorrect, but then, as they see more of the video, maybe they move the slider back over to the other table and they become more and more certain about the correct goal. We have to introduce some new metrics that take advantage of this continual measure of certainty. So here is one metric called clarity, which is essentially the area under the curve. So how overall, how well people were able to infer the robot's movement. We have another metric called envelope, which says how long before the end of the trial were people certain, or at least reasonably certain above this threshold of the correct goal. So how long were people ready for the robot to come to their table? And we also have moments of confusion. So how often did people switch which goal they thought the robot should be going to, or was going to? And with these metrics, we were able to assess what our particular robot navigation algorithm. But what's really relevant for this workshop is that we're hoping to combine these two things. So we're hoping to take what we've done with SockNav Bench, which simulates these kind of pedestrians moving in large scenes, and add these new measures that I just talked about, these 3 different metrics, into the assessment, and then also add these new scenarios. So one thing that a lot of social navigation work has primarily focused on is crowd movement, but we're really interested in these other kinds of environments, like seated at a restaurant, or seated in an office, or standing at a workbench within a factory, right? So these environments where people aren't necessarily moving around, but the robot still needs to be producing some kind of legible motion. So this is ongoing work, and we're trying to collaborate with Google on that. So I wanted to end with a couple of open questions, because I think that we don't have everything solved, and there's a lot of interesting points. The first is that context is really important in social navigation. So for example, in that hospital delivery robot, it should yield to people who have trouble walking, or physicians who are clearly responding to an emergency, and much more than it needs to yield to somebody who's pushing a laundry cart down the hallway, or vice versa. If the robot is delivering urgent medical supplies, it should take the right of way over other people much more than if it is delivering laundry supplies, right? So the context of what's happening for the navigation matters a lot. And so that should dictate which scenarios we include in our benchmark systems. Also, the big shortcoming between of SockNav Bench is the fact that these are purely replay scenarios. So we took real human movement, we replay them, and we essentially assume that a successful social navigation algorithm will avoid perturbing the existing human movements. But the humans in our simulation are not responsive to the robot's movement, whereas in reality, people would be responsive. People would change their trajectories based on where the robot was. So there's a balance to be struck between our kind of replay metric and dynamic simulations, which rely on potentially suboptimal models of human movement. Another question I was hoping that we would get to discuss, and we'll have time for Q&A, is how far can we push simulations? We all work with robots. Robots exist in embodied environments. It's really important that they are embodied. And so at some point, I think we're going to reach a limit of what simulations can achieve, but it would be really interesting to talk about how far we can actually get there. And the last point is, what even should our metrics be? So I introduced a bunch of different metrics earlier that had to do with the quality of the robot movement and collisions. And I also talked about human experience metrics, but there might be other metrics that are more important that we can integrate into our benchmarks and therefore drive people to try to optimize. I think that is it. So just to give you, again, a summary, what you should take home from this talk. I talked about SockNav Bench, which is a realistic simulation framework for assessing different kinds of social navigation. And here's the associated paper for that. And I also talked briefly about how we might measure user experience of social navigation from first-person perspectives, also in simulation. And that's the associated paper. So thank you for your attention. Yes.
Great talk. We talk a lot about obviously.
Thank
I
you.
keep shocking you.
Just leave the mic with.
Yeah. So I am curious, particularly in simulation, what are some of the kinds of parameterizations that you have over the simulation? So I could see it's like maybe number of people in a crowd density, but I'm curious in particular through the lens of like cultural parameters. So people who are walking the right versus the left, I'm still confused outside. I don't know the answer here.
It's not. There's no answer as far as I can
Fantastic.
tell.
Okay, but like, can I get that in simulation? Can I take data from one place and say now we're going to have left side of the sidewalk walkers, right? Contact versus non-contact cultures. Those kinds of things. Are those parameters that I can jiggle in simulation?
That's fantastic. So in simulation in general, yes, those are parameters that you can absolutely jiggle. Within SockNav Bench, so I'll say the data sets are drawn from a variety of environments, both US based and European. I don't think we have Asian representation or anything in the Southern Hemisphere. That's just a function of which data sets are out there, what universities are producing these data sets. We have 4 different data sets, and they represent different amounts of crowd densities. We also have robots moving, starting from different start points. So we try to be representative about the scenarios and have a diverse set of parameters for things like human movement. But you're right that culture is part of that context that I mentioned that's really important to include. I think even the weather, right, could be something that affects how people move, whether there's ice on the sidewalks or not. So all of those are elements that we could add to this simulation. Right now, we are diversified in terms of number of pedestrians and some different countries and cultures, but we're not fully representative yet. Yeah.
So it seems to me that with the way that the measures have been laid out, this would try and optimize a navigation strategy that replicates human behavior, which is not necessarily the goal. It could be a goal, but it's not necessarily the goal.
Absolutely.
Any comments on that?
Yeah, no, I think that's a really important point. And I think I'm a big proponent of let robots be robots. Like robots don't have to be humans. Like they can move in different ways as long as they are legible to humans. That is the big downside of this replay metric, is that it sort of requires it assesses the robot in terms of how well it integrates into this existing human environment. I think that this is one direction that we should take. That's why we kind of combine with SeanNav Bench, because SeanNav Bench gives us a chance to have the robot interacting with the simulated humans. And so that gives a different perspective. So I think that both perspectives are valuable.
So you mentioned that it's clearly not feasible for us to run a fleet of robots out in the world and collect perfectly valid data. But I'm curious, since there are parts of the world where service robots are kind of commonplace, if we imagined in 10, 15 years, if that was already the case in the US, for instance, would the way that we think about this change a lot, or what would be the role of simulation then?
Fantastic question. I think that is always true. I think that we're seeing this a lot now. The way that people think about robot interactions has changed even in the last 10, 15 years based on the robots that we have out today. And you're right, there are, for example, sidewalk delivery robots, even in Pittsburgh, that are, rolling around doing navigation. There's the tub robots, which have been around for a long time. I think that the perspective on what metrics we wanted might change as people become more familiar with robots. Maybe, for example, we wouldn't be so concerned with minimum distance to collision, because we would assume that people can merge cleanly and are comfortable moving around robots. But I think that the basic need for simulation probably will not go away, because it's a really fast way of testing a lot of different algorithms. The other benefit is it lets us create potentially very challenging situations where, for example, collisions might be likely. And it's something that we wouldn't want to necessarily test in real life if we can avoid it.
So can you go back one slide to your
Yeah, my
questions?
questions.
So
You want to
oh yes, for the balance between replay and dynamic simulation. So I think about this in 2 ways. One is adding noise or variation to the patterns that you already kind of put into the simulation. And the other is reactive, where now there becomes some kind of interaction. Are you talking about both of those aspects as things you would want to include?
Personally, and I'm actually curious what my students will say about this, because they thought a lot more deeply about this. Personally, I think the second one is more relevant. So the issue with perturbing the existing movements is that the existing movements are useful because they are examples of what actually happened. So perturbations would have to be careful not to move us too far away from that reality. But if we could have those existing movements as a baseline and then have interactiveness within the simulation as well, I think that is the ideal kind of balance that we could strike. I'm not exactly sure how we get there, because as soon as we have interactiveness, we're making some assumptions
Mhm.
about how people are moving, and we come back to that chicken and egg problem.
I suppose you could model an actual interaction,
Yeah.
right? With, I'm trying to get there be a way to take the human reactions to the system as part of what is getting replayed,
Yeah.
if it occurs.
Oh, like if we actually had people, we had a robot in the scene and we had
Yeah.
people responding to that robot and then try to like
Use
model.
that as
Yeah,
part
yeah,
of one of your.
yeah, that would be good, and that would be a way potentially of taking a small amount of real data of a robot in the wild, so a small amount of our ideal situation,
Right.
and scaling it up using simulation.
So how it is typically modeled to follow where like if the robot is confused between following a navigation social cue versus completing its goal. So in that case, what would it decide to do? And like for example, in a restaurant, if a mobile robot is serving, and I've seen this in action that if the path is blocked, it just it's the same in the factory automation as well, and it's kind of, like, they have reached this far and it's just sad to see that it just stopped.
Yep.
So what, in that case, what's typically done right now and what should be aimed in the future when we
Yeah.
like, develop an algorithm?
Yeah, that's exactly right. So we have this freezing robot problem where it reaches a point where it can't decide, can't safely move in any direction, so it stops. And stopping is often the safest default, and so that's why we see that happen. How the robots resolve that really depends on the algorithm. I've seen situations where it's sort of a hierarchical thing, so the safety is the most important, and then achieving the goal, and then adhering to social norms or something like that. But it really depends on how the designers want to produce that. I think that there's a lot of value to be found in social cues. I think actually that we as humans respond a lot to the social movement of others, and the robots actually could do well to also be responsive. So for example, when we're navigating, we form lanes, which is that when people are moving in the same direction as us, we move in behind them. And so this is what happens here. Apparently, like, we often form lanes behind people, and so you have these lanes that are moving in different directions. And if a robot was capable of doing that, it wouldn't necessarily need to be totally cognizant of all the other social norms, because it would be using the humans around it to kind of figure out the norms for it.
So thinking about the social cues, what about the cues that we all take up when we're dealing with either non-sighted or pedestrians who need assistance?
Yeah.
And how much of that is available in the replay and in the simulation?
That is a fantastic question. To my knowledge, there are no pedestrians in the data set who are low vision or need assistance, but I can't say that for sure. My student who has looked at all these videos would definitely be able to tell you. But I think that's a really good question, and that kind of goes to the idea that there are the sort of like non-normative case people, like a lot of non-normative case situations, right? So people who use wheelchairs, people who use walkers, people who are pushing strollers or dragging luggage, which we have all experienced recently, I suspect. So those are definitely kind of components that we should integrate into this situation. I think like the pushing stroller, dragging luggage is a particularly interesting example because it expands the person's profile. And I don't know how many social navigation algorithms are considering that as an extension of the person or not.
One interesting thing that I recently observed was when we talk about replay and dynamic situations, when people tend to navigate around robots, even like small delivery robots, they have this novelty effect, so they want to stop it. Some people don't even bother with it, but some people just feel it very interesting. And how to model that is, I think, very hard, because it's a very random thing that they just stop it and try to understand it. Sometimes even kind of get cute and start talking with it. So
Yeah.
how to model that? I wanted to ask that.
Yeah,
Comments on that.
that's a great question. And sometimes they stop it and they find it cute. Sometimes they stop it and they try to trick it or they hit it, right? We've seen videos in HRI of children hitting robots in malls. Like this, there's a lot of interaction that not what would happen when a human is there. So I'll make a shout out to Aaron Steinfeld, a collaborator of mine who's currently, and he and his team are currently collecting a large data set of people navigating in a space with a first person view of a cart being pushed by a person. So the cart sort of represents the robot. It's not fully robotic, so people aren't treating it like this novel agent, but it is a more, it's more representative of what form factor and kind of presence a robot might have than another human being. And so that might be a step in that direction of modeling how people are interacting with the system.
I think that's time.
Okay, I'm happy to answer more questions during the
Cool.
coffee break.
Thank you,
you.
Henny.
Glad we got to